Atomic Theory Part 2. There are 3 parts to the atomic theory lessons, starting with the Thomson-Rutherford model in Part 1. You must know the difference between the Thomson and Rutherford model and the critical experiment that allowed us to choose the better model. Atomic Theory Part 2 goes more into the philosophy of science, showing how all models are essentially wrong and provisional, meaning they are subject to change. Atomic Theory Part 3 goes into the techniques you have to master to be successful at grade 9 and 10 science. This leaves the Part 2 lesson to be more of a transitional lesson, and there is nothing particularly testable here. It's just important as a general guide to understanding the purpose of models in science. You will be able to explain the structure of the atom even if you don't see this particular lesson. You need to be able to describe the difference between Thomson and the Bohr-Rutherford diagram, construct a Bohr-Rutherford atom using the orbital structure of 2, 8, 8, 8, or 18, discuss the provisional nature of models, and be able to discuss all models are wrong with examples.
Do you want a chocolate? I could eat about 1.5 million of these. My mom always said life was like a box of chocolates. You never know what you're going to get.
This was one of the most famous movie metaphors of all time. It's been lampooned many times. Life is like a box of chocolates. You never know what you're going to get. This would be what we call a metaphor or simile. And a model is something very similar to that. You are taking something which is not the thing you are talking about and using the attributes of the model to explain the thing you happen to be talking about. Models are the metaphors of science. The misunderstanding is most people think of all models in science as being scale models and complete descriptions of the thing in nature we're talking about. And this would be like misunderstanding this. Forrest Gump's model is life is like a box of chocolates. His intent with the model is to explain that life and boxes are mysteries until they are opened. But this model could be used to predict several more characteristics of life if you don't know what the model's limitations are. And this model, the Gump model of life, would also imply that life will come shrink-wrapped. That if you can read labels, there are no surprises, because all boxes of chocolates have that little mystery label sheet that will show you a squiggly little picture of one of the chocolates and what you should get when you bite into it. If you are lactose intolerant, you will find life to be a gigantic diarrhea show, if you get my drift. It also implies that life comes in a rectanguloid volumetric container composed of wood, cellulose, and various waxes, dyes, and adhesives. This model seems to make some really strange predictions about life. Not just, you don't know what you're going to get. This forces us to come to terms with the model's predictions with about 3 alternatives. The model's not literal, dudes. It's metaphorical. It was only intended to talk about the one thing, mystery. And the author of the model had no further intentions than that. Stop going too far with the model. This model is wrong because only one prediction out of 5 is valid. So we reject the model and say life has nothing like the characteristics of a box of chocolates. The third possibility is this model, we didn't realize it at first, it's posing 4 new intriguing paths of investigation. Our universe might be in a gigantic cardboard box. And if this is true, there should be an enormous planet-sized chocolates out there. This means that if there are giant planet-sized chunks of chocolate out there, the chocolate market on Earth is going to collapse. Sell all my shares in Hershey Chocolates now! Where are we going to go with this? What path are we going to take with this model? And this is something the scientists who create the foundation for our learning struggle with. The textbooks are good at presenting the model that won, not the battle that took place before the model that you are taught as truth emerged. Let's look at a real-world example. This is Newton's law of universal gravitation that he put together in the late 1600s. It looks kind of scary, but by grade 12 you'll be able to handle this model. Many of you could compute with it now. It basically says we take the gravitational nature of the universe, multiply by the two objects that are attracting to each other, like the Earth and the Moon, and we divide by the distance between them squared. And this will tell us how much they're pulling on each other, in newtons or in pounds of pull. This is going on between you and the Earth right now. The distance between you and the Earth is from you, the center of you, to the center of the Earth. I'm going to get rid of the things that won't change. The force is proportional to the inverse distance squared. What this means is, if you double your distance from an object, the force will change by 1, 2 squared. This means the distance between you and an object is going to highly determine the gravitational pull. And if the distance between you and an object begins to head towards 0, 1 over 0 is infinity. Newton's equation predicts that if you get close to a massive object, really close, distances of like millimeters away from the center of mass, the force will become infinity on you. And this was rejected at the time as just a curious misprediction of the model. Well, don't use the value of r is equal to 0 because this creates a situation that it predicts that there's going to be some like tiny little singularity, an isolated spot in the universe that would have infinite gravity. It would be this like, and it's stupid to think that somewhere in the universe there could be this incredibly tiny object with infinite gravity that would suck everything else in around it like light itself, and it would be like some kind of black hole in space. I mean, how stupid is that? That prediction clearly is a flaw in this model. 3 centuries later, we get a picture of that flaw, that black holes do exist, and Newton's flaw in his model turned out to be a truth those scientists couldn't accept yet. We're an outlandish prediction of a model turns out to actually be true. And Einstein modified Newton's model to accommodate these black holes. Then we have Stephen Hawking's come along and he modifies it further, that black holes can actually evaporate and things can escape from black holes under the right terms. So we're not done with this model yet. We just keep tweaking it. And this leads us to what I really want to talk about. George E.P. Box. All models are wrong, but some are useful. And this is something I would like you to embrace in science. All models are wrong, but some are useful. It was a certainty that the Thomson model was wrong, and that the Rutherford model better described reality in that the atom was composed of a dense positive nucleus with the electron far, far away in orbit. But the Rutherford model also had a prediction. Just like Forrest Gump, just like Newton, it had a prediction that seemed impossible. Rutherford's orbital model has a serious flaw. It says we should not exist, that the universe cannot exist the way his model works. Because electrons travel and orbits decay, the electron should wind up crashing into the nucleus, and when positive meets negative, matter shorts out. The Rutherford model could not account for that. As an extension, it is well worth reading the Wikipedia entry on All Models Are Wrong. Here, George Box uses an example that directly relates to thermal expansion. In grade 11, you will study the universal gas law, which gives you a formula to predict the new volume of a gas when heated. And here is his comment below. Around the same time that Bohr, Rutherford, even Einstein were working on this, there were people that studied large-scale matter. We're not talking about single atoms, we're talking about the light coming off the sun. When you heat a piece of iron until it's glowing red, then orange, then yellow, then white, how come it never glowed green? And they wanted to study the light coming off things when they heated. This is called blackbody radiation, and it's the spectrum of light coming from a glowing object, and we will see it in ecology and optics in grade 10. It turns out that if energy could be freely emitted and transferred from an object on any wavelength you wanted, that everything in the universe would start emitting radiation in a blast of ultraviolet light and disappear. And they called this the ultraviolet catastrophe because their model worked really well. It could predict the color of light you would see at specific temperatures. It would allow us to take a picture of a star and tell you its temperature. You can use it on cameras. You can look up what's called color temperature on your cameras. Unfortunately, the theory also predicted that everything would start emitting energy, blasting it off, and quickly run out of energy and vanish. And they weren't sure how to account for that. So the solution was to realize that nature could not emit any energy it wanted, but the energy could only come off an highly defined spectrum. And that would be the difference between a trombone and a trumpet. The trombone can make any note it chooses, even in between, where a trumpet or a piano has no choice. It can only emit sound at specific notes. And this is what we call quantum physics. You cannot give people money in between the coins. You could give the person $1.95, but it is not possible in Canada anymore to give a person $1.93 in terms of physical money, because the quantum, the single penny, has ceased to exist. The smallest block you can move is 5 cents. Now, this gave a guy the idea for the atomic model that maybe these electrons could simply not start spiraling into the nucleus. They couldn't go from a high energy orbit here to a lower, tighter orbit because it was not allowed. Like saying, hey, can you play me a note halfway between A and A sharp on the piano? No, it doesn't work that way. Another man, Niels Bohr, came along and he borrowed this idea of quantized energy, or quantum, that there are little blocks of energy and you cannot have something in between. Tim Hortons is not going to allow you to buy half a donut. You must buy them in quantum. You must buy them 1 donut, 2 donuts, 3 donuts. So the electrons couldn't spiral in and crash. They were locked in to one of these energy lanes. Low energy orbits are tight to the atom, middle energy orbits, high energy orbits. And the only way it could change an orbit is by vomiting out all the energy at once or taking it in all the way at once. Nothing in between. And in fact, they don't even exist in between these orbits. So the electron cannot move from here to here by going and like a coin going down a funnel. And we're going to study 4 of these lanes. This mostly solved that problem. And this modified orbits, where these orbits were quantized or defined, became known as the Bohr-Rutherford model. And the guy who provided the equation governing it was Albert Einstein. He never got his Nobel Prize for E equals mc squared. That was his graduate paper, and people were not that actually impressed with it. It took them about 30 years to really realize what he had done. He won the Nobel Prize for explaining how energy in a solar cell was absorbed. It turns out not only were the orbits locked into position, but these orbits were not like the rings of Saturn or the asteroid belt. Both of these are full of thousands of orbiting fragments. There were specific rules for each orbit. Orbit 1 can only have 2 electrons. Orbit 2 and 3 can carry 8 electrons. Orbit 4, it's 8 and 18. It gets kind of complicated. It's kind of like it's got opera booths and floor seating at the same time. And we're not going to really dally into the 4th orbit much. You'll get into that in grade 10 and 11. This is an example of quantized seating. You can't sit anywhere you want. Here's our nucleus, and the electrons have been ordered to take seating like this, and the seating must fill from the center out. Here's another theater in the round. You have the actors can go here and mill about all they want in this nucleus, but the participating electrons have locked-in seating positions, and they are ordered to fill the seats starting at one location out. And remember how I said the 4th orbital was like 2, 8, 8, or 18? That's kind of like saying this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's the 11th orbit, but it has a lower level and it has an upper balcony level. And that's why I said the 4th orbit is kind of like 8 and 18. It has an upstairs-downstairs arrangement. You'll get to that in grade 11. So think of an atom like this now. We have this nucleus, which is like a mosh pit, and this quantized seating for the electrons, where you must take the assigned seat starting from the center out, and you are not allowed to position yourself between the rows. In fact, you can't even exist between the rows. You literally just transport, go instantly between the rows, and nobody ever saw you get up and walk. So it's a really strange structure. This is non-quantized seating. This would be the Saturnian model of the atom, where the electrons were free to just mill about like in a mosh pit. There's another example of non-quantized seating. The center nucleus is supposed to be free of electrons, and the electrons are just this swarming sea, and it turns out that's not the way atoms are constructed. Atoms are constructed more like the inner part of the solar system, not like this mess out here. Saturn itself, oddly enough, shows some quantized arrangement. You have debris that's here, but for some reason debris is never located there. It has gaps. So it turns out in Saturn's ring on a time lapse, you can see all sorts of forbidden zones where nothing orbits. Right? There's no rocks in there at all. This ring stays open here. But this has to do with gravity reasons in the debris field, not a fundamental law of nature like the atom. This is what happened within 50 years. Thomson's first model, a very well thought out model that worked very good at the time, envisions equal numbers of protons and electrons. And he was able to knock the electrons out, prove that they were a particle, and just figured they were studded in the positive charge. Rutherford conducted better experiments, and he came out with no, in fact, the positive and negatives were isolated from each other, and that very little of the atom was solid space. Only 1 part in 2000. It was almost completely empty. Then Bohr came along and said, almost right, but these electrons are not really orbiting. They're like in seating arrangements in a round theater, and they have a very highly specific seating arrangement. By grade 11, you will modify it again to this wave model, and the wave model is incredibly beautiful. So why don't we just start down here? Because each of these models is getting more complex. So why would you start with a wave model if you can get away with this one? But if you want to understand chemistry, like why water forms, you have to be at this model. These two models will not help you understand why the formula H2O exists. This model will. This model will help you predict other things and the shape of crystals and all that part of beauty, and you need that for grade 11 and beyond. So this is the idea of the models get modified with the amount of complexity we need, and we stop when it's good enough for our current needs. You are only going to study this model in detail until grade 11. So here is your grade 9 and 10 structure. Proton and electron count are the same. Neutron count has no bearing on the others. Neutrons do not contribute to chemistry. Protons occupy the nucleus only. There must be an equal number of electrons surrounding the nucleus with the orbits of holding a maximum of 2, 8, and 8. And we rarely stray into the fourth orbit in grade 9. Everything else is now going to be in that package I gave you. How much of what I just showed in this lesson do you need to remember and be tested on? Nothing. This was just the transitional lesson. But by the end of this assignment, you're going to be able to understand why H2O and not H3O is the formula. And that will be the predictive power you will be given. And I'm going to go into crystal forming as an extra because there's some just gorgeous, beautiful things out there in the world I would like you to see. So do not expect a test question on any content of this show other than why all models are essentially wrong. So you could use the Forrest Gump example, and that would be sufficient. And we're talking about 2 marks on the entire course. Okay? So if you want to forget you ever saw this lesson, fine by me.